Okay, welcome to the 6th practical session. Today we'll again talk about arrays, pointer and strings, because I think you can't talk enough about them.
So if everyone has taken their seat, then we will start with organizational matters again. Today there will be a lot of things that we release, assignment 3, homework 3, coding session 3. Yeah, and then as you already described, we talk about dynamic memory, stack, heap. So we basically continue with the last practicals. We again have a lot of pictures today that you can visualize the memory, and we will also program a bit today. And there is something hidden behind this bullet point, everything you need. Yeah, this is the most important thing of our practicals today and maybe of the whole course. So yeah, that's important.
And I think we were mistaken, it's the 7th practical session.
Ah, it's the 7th already, yeah? Okay, organizational matters. That is your part.
Yes, okay. So homework 3 will start today, and also the registration for the coding session will start today. And this time, please register for your coding session where you're sure you have time already today or as soon as possible, because with coding session 2 in the last week, we were fully booked, but in the first 2 weeks there were only half full slots, and I think it's really not that good for our tutors if they didn't have to do additional coding sessions, even though we held enough coding sessions.
And many of them were empty, so yeah.
And for homework 3, you will participate in a study of ours, and it will be with debugging and memory visualization, and I hope it will help you. I think, I have an extra slide. So the first note, I think that this homework can also help you with the exam you have to take, because they are very similar, or maybe not as complicated examples at the exam, where you will have to do similar, really think about how pointers work without really executing the code. Because this is a study, we'll just grade homework 3 on completeness and not correctness, so it's okay if not everything is correct, but please still take your time to do it carefully. And also, for the first and the last part of the homework, no external tools are allowed, and you will see later, and everything will be described on the Teach Center, but please also do that. It's okay if not everything is correct, but this could help us understand how well we explain pointers, how well you get these concepts, and maybe so we can optimize our course in the future with what misconceptions you have. Everything will be explained more detail in the homework, and please read through all the text we've put there up front carefully so you know what to do and when to do what. Can you go to the Teach Center?
Mm-hmm.
Yes, so in the Teach Center for the homework, you're in 2 different groups. You don't need to worry about them. We have here the link for group A and group B. One of those 2 links will work. The other one will display just an error message. Just do the one that works.
If both show an error message, then please write us on Discord.
Yes. But I think right now they will display an error message because it's not released yet. But today after the lecture, if both of them show an error message, then you can contact us.
Yeah, and that's not everything that we released today. We will also release assignment 3 today. Same procedure as at every assignment. At 18:15 there will be the kickoff video on YouTube by Lena. The repositories are maybe already available, maybe in 1 hour, maybe in 2 hours, I don't know, but at some point today they will be released, and you have again 2 weeks time to complete the assignment 3. So it's Wednesday in 2 weeks, the 11th of December. And followed by the deadline of assignment 3, there will be then assignment interviews for A2 and A3. So this brings me to the point of assignment 2. Next week there won't be assignment interviews for A2, but probably on Wednesday, Thursday, Friday, we will still upload the grading of assignment 2, that you have an overview before the A3 deadline and that you can maybe fix some mistakes that you did in A2 to not do them in A3 again. Okay, yeah.
Okay, so let's continue with a recap from the lecture 2 weeks ago. I hope you can still remember something. Let's start with the memory layout of your typical program that runs on your operating system, in our case Linux. And maybe this will also explain a bit more why we draw the stack in our illustrations from the top. This is very similar to an illustration you've seen last time in the lecture. And on the left here, you see I wrote memory with these quotations marks, because for your program, it always seems like that it has access to all the memory your computer has. But these are just tricks your computer plays on your program. So that's not actually the case, but it seems like it is to you. So basically, your program has access to these addresses that start with 0x7f, if you can read this, and then 16 of those hexadecimal digits, because then this will be 64-bit. If you look at your memory, so the memory of your program, you can see that the stack will always be near the top and grow downwards. It won't be in the same location every time, but near the top, and it will grow downwards. And then the heap, so our dynamic memory, which we learned last time, is more in the middle and grows upwards. Then there's also a separate region for global variables, constants, and your compiled code. Yeah, so if you have an address, maybe here note that your stack addresses are always these very high values and the heap addresses are mostly a bit lower. So yeah, if you are debugging, this could be a nice thing to know. But more importantly, what is on the stack and what is on the heap? Well, everything we did until dynamic memory was on the stack. So the local variables, the stack arrays, any other ideas?
Yeah, basically that's what we've seen so far.
Function parameters. So yeah, everything you had access to, all the variables were on the stack. But now we can also use the heap. And the heap, you can acquire memory there, so a region of memory, by explicitly calling these dynamic memory functions. So for example, malloc, calloc, and yeah, another difference, which might cause some confusion, is that on the heap, you always need to manage the memory on your own. So all of this needs to be done by the programmer. You need to think about how much memory do you need, and then also how long do I need it, and when do I free it or give the memory back to your operating system, basically. And you need to take care of that, because otherwise, yeah, this memory just won't get deleted until your program stops, and then you could run out of memory. And as we've seen on the stack, you won't need to do that. So if you have just a variable on the stack, just an array on the stack, as we have seen in these drawings, we call a function, we have some variables there, and once the function returns, all of this is automatically deallocated or deleted.
Maybe I can also add a bit to that. Why do we have this design? Because it works, because we need to have some conventions, how we structure the memory. And this was a practical thing to do it this way. That's why we have the stack on the top and the heap more in the middle, and then the compiled code and the global variables at the very bottom. It's convention. Why does it make sense that everything of these things needs to be in the memory? I mean, for the variables, it's clear, because I mean, they need to store something, and we need memory to store something. But also it makes a lot of sense that the compiled code is stored somewhere in the memory, because your computer must know what it should do with what values. And for that reason, we need the actual code somewhere in the memory, and we also need the variables.
Yeah. And maybe also why are the global variables and constants somewhere else? Well, because most things on the stack don't last forever, because the stack always shrinks and increases again with its size when variables get added and deleted automatically. And these constants you of course have access during your entire lifetime of your program. So yeah, you want these to be always available. Okay. Then let's continue with the recap about dynamic memory. And we have seen these functions, basically how you can manage this dynamic memory that you need to take care of by yourself. So maybe let's start with malloc, where you just pass the size of bytes you want to allocate on the heap. And then it will return a pointer for you where you can then access this block of memory. But as you can see, these are sized in bytes. So you need to be careful of how much memory you really need, how big your data types are, etc. Then calloc, very similar to malloc. It just clears the memory with zeros before you use it. Could be useful. Also, there is this extra count and size of one element parameter. So in malloc, you need to do this on your own. You need to take the size of one element and multiply it with how many you want. And with calloc, this does this for you. But it's not really a difference. And then, if you have some dynamic memory and you want to increase or shrink this memory, so for example, you have an array where you store 100 characters and then suddenly your user enters more than 100 characters, well, then you need to increase this array to store more. And then, maybe also very important, that you free all the memory you have. So you just pass this pointer you got from malloc or realloc or calloc and pass it to the free function, and then this block of memory is gone. Yes. And also, all of these functions except free could return the null pointer. So they could fail, for example, if you don't have any more memory, or if you try to acquire too much memory, which your system doesn't have, then all of these could fail, and they fail by returning the null pointer. So let's look at a simple example. So what do I have here? I just made some variables on the heap, some variables on the stack, just to illustrate how this could look on the memory. Yeah. So I have this one variable in the main, then I have this pointer to the heap on the main and this array in the main. And if you look at this in the illustration, we see, okay, these local variables are directly on the stack. Also, this heap pointer is on the stack, but the actual data where it points to lies on the heap. So with this malloc here, where we passed in size of int times 3, because how much bytes do we want? Well, we want 3 times the size of an integer, and then malloc returned us a pointer to this block of memory on the heap. And this pointer is then, of course, in the stack in this local variable, but it points to somewhere that's not on the stack. And then I have this local array, which, just as we've seen, is on the stack. Then we are calling this function, and actually this illustration is somewhere in this function, how this memory would look like at the end here. And in this function, again, I allocated this heap block of memory, which has the size of an integer times 2, so we can store 2 integers there. And again, we see, okay, we have this heap pointer 1 in this function, which is a local variable stored on the stack, and it contains the address of such a block of memory on the heap. And I have drawn this with a pointer as we have used to, somewhere to the side here. And maybe, so this is so you can get a better overview. I drew the heap on the right side and the stack on the left side. Of course, in memory, this is just one sequence, and the stack is at the top and the heap is at the bottom. Okay.
Any questions?
Yes?
Why do we need the integer pointer cast before malloc?
Okay, so why do we need this caster to integer pointer? I don't know if you really need it, if it's a warning if you leave it out.
No, you don't need to write it.
Yeah, but I do it because malloc returns just a pointer to something, a void pointer, because it doesn't know what type of memory you want to have there, what type of variable you want to store there. And so because I'm assigning it to an integer pointer, because I want to store integers there, I'm casting it to an integer pointer.
But if you don't write it, it's the same at least in C++, for example, which you will learn in the summer semester. There will be a difference there. You need to cast, but here it doesn't matter.
If you don't write it, it will automatically be done by the compiler. So it will still happen, but just you don't see it. But we have said that we need to free memory that we have on the heap. So maybe at the end of this function, instead of just returning, I should add this free here to free this heap pointer again. And well, how can we imagine this? We can imagine that this free just deletes this block of memory on the heap. The same values could still be there, or they could be owned by some other allocation of your program. So there could be completely different values there. But a thing you could note is that this heap pointer that we have here, this one in the function here, still points there. But it's not valid, and it's not a valid memory region anymore. Yes, and we'll see later that this can end badly.
Yeah, I mean, we can again see like the structure of the stack. So why is it called stack? Because we stack functions on each other, well, like in the inverse order, because it's growing from the top to the bottom. But we have one function. When we call a function, there will be the stack frame of the next function. So like the main function is at the very top, and then you have the stack frame of the function called func. And within this frame, we always have the local variables of the function. And the heap is kind of not structured in this way. This is more freely structured, and you just go there, I want the memory, and the heap gives you the memory. And at some point you say, okay, please heap, I don't need your memory anymore, take it back. But the structure of the heap, it is structured, of course. There must be a concept behind it, how to do this. But for us, there is no apparent structure at the very beginning. These blocks of memory in a heap can be everywhere there. There could be space in between. It could be that we have one block of memory and then the next block of memory directly afterwards. For us, there is no structure. You will later learn in other courses how you can structure that.
That's why I drew these dots here, because we don't know if there's anything in between of both of my allocations I did here, if there's space, if there are maybe other allocations that happened elsewhere. We just don't know.
And one last thing I want to say, please note that the pointer that points to the heap, also the address that we store, this address is stored on the stack. So the pointer itself is a variable that lies on the stack, and on the stack we store an address. And this address is then, luckily, hopefully, the right address on the heap. And then the memory block is on the heap, but the pointer itself is stored on the stack.
Yeah. So this heap pointer 1 here in this function, as we can see, it's on the stack. Okay, so we now know how to allocate and then maybe free these blocks of memory we can get on the heap. But if we want to do anything more complicated, we might want to look at realloc. So, okay, they are just, if we just malloc with one size, this could be useful, but it's not very different from what we did on the stack already. But now realloc really gives us more power on how we can handle our memory. And again, I have then this excerpt here from the man page, as you did last time, and we'll just read through it and then maybe try to interpret this. The realloc function tries to change the size of the allocation pointed to by pointer to size. So realloc gets a pointer, which is this pointer here, and it tries to change this allocation that was previously allocated by malloc or calloc, or maybe another realloc, to the size specified to the realloc function. And it then returns a pointer. But, okay, it returns then a pointer. Why does it return a pointer? Well, if you read on, if there's not enough room to enlarge the memory allocation pointed to by pointer, realloc creates a new allocation, copies as much of the old data pointed to by pointer as will fit to the new allocation, frees the old allocation, and returns a pointer to the allocated memory.
That was a lot now.
Okay, so why does it return a pointer? Well, if we want to increase this allocation that we have, but directly after our allocation there's another allocation, then we can't just say, okay, you get this memory, because we can't change this other allocation. Therefore, realloc needs to create a new allocation with the new size that we want, and then copy all of our data that we had in our old memory block into the new one, and then return us the pointer to the new memory block that's actually bigger than the memory we wanted before. Or maybe smaller if you decrease it.
Maybe to make this even more concrete, you have an integer array of 5 integers, and you also allocated a character array of 4 characters. And now you want to increase the array of the integers such that we have 10 integers contained instead of just 5. But we have the situation that there is the block of memory of the integers, and directly afterwards there are our characters. And if we would increase the integer array to a size of 10, then this would create a conflict with the character array. And for that reason, we cannot increase the size of the integer array. So we need to look for space for an integer array of size 10, then copy the 5 values of our already existing integer array to the new integer array of size 10, and then we can again free the array from before of size 5.
And of course, we somehow need to be able to know where this new memory location is if realloc gave us a new memory block, and that's why it returns a pointer. This might be abstract to visualize in your heads now, so let's look at an example. I have this code here too. So let's just say I have just a simple example where first I have this malloc here, and the malloc just this constant size times the size of an integer. So I'll be able to fit size integers into this malloc call, into this memory the malloc returns. So I have this my array here, and when I'm here, where this arrow points to, so in the first line, after this line, the address of this heap memory block, malloc returned, will be stored in my local variable my array. And if I follow this pointer, we'll get to some memory block on the heap, which is the size we specified here. Note that my large array wasn't initialized yet, so it just contains garbage data, any values we don't know. And just for demonstration purposes, now let's assume that directly after here, on the heap, there's no space left to resize our memory allocation. So what happens now if we try to realloc my array? So I pass in here into realloc the pointer my array, which points to my memory block, and then the new size I want. and I want to double it in size. So I'll pass this here. Okay, so what does realloc do if there is no space to resize? Well, it frees, no, okay, other way around. It allocates a new block on the heap, which is bigger. So I drew this slightly bigger, if you can see this. And then it will copy all of the data we had in my array, so in the old array, into this new block. And then afterwards it will free the old memory block. And then it will return us a new address which points to the new memory block on the heap, which contains the same data as before, but this memory block is bigger. So we don't need to copy any data around manually, everything is done. It will look like to us that in this new address we have the same array, which is just bigger, but it was actually copied if we didn't have space for it. And again, as we can see here, the old memory block is freed, but we still hold a pointer there.
Any questions? We will do a programming example on that with even more visualizations. But are there any questions right now? Yeah?
And in the definition, as much as possible, values are put there.
Mm-hmm.
Yeah, all that. But you said all of the data of this one. Because is there a possibility that some data gets lost because it's a copy and then it's just spread and maybe not well?
Okay, so the question was, here it says, does it tries to copy as much data as possible to this new memory block, but I just said that it will copy all data to the new memory block if somehow this data can get lost. And well, no, we can always know that if realloc returns us a new pointer which is not null, so it succeeded, then all of our old data will be there. The reason why it says here that as much as will fit to the new allocation is that it's possible that we want to shrink our array, and then not all of the data we had in our original array will fit into the new allocation, and then it will just copy over how much fits into this new allocation. So yeah, even if you just shrink your array, it's of course not guaranteed that it will stay at the same location. It could move it to some other place for some reasons, and then it will just copy as much as fits into the new array.
Mm-hmm.
Yes,
further
good
questions? Question. Yeah, further questions? Well, continue. Now you have 3 minutes more or less break until we come to the next very important topic, but now we just talk very briefly about Valgrind, so clean your heads a bit. I don't know how to tell this in English correctly, yeah. So Valgrind, I think most of you used it at some point during the assignments. Mainly for the last reason that we have here in our list, for the uninitialized variables. They were a bit, they occurred sometimes. You got these Valgrind errors and you didn't know why they are there. Valgrind in general is a tool that detects memory errors and memory leaks.
On the heap. On the heap.
On the heap, mainly on the heap. Yeah, so the uninitialized variables are on the stack, but most of the stuff is only checked on the heap. So if you did something wrong in assignment 2, you had an array of size 5 and you wanted to access the 6th element, then Valgrind was probably not complaining. But on the heap, Valgrind works very, very, very good. What does it do? Yeah, it checks everything regarding dynamic memory. So it will tell you if you allocated memory with malloc and didn't free it. It will tell you if you allocated memory and you free some memory which you did not allocate or whatever. You just say, please free me something which you never got. Yeah?
You always have to pass the pointer to free that you got back from malloc. So it can't be any point in the memory block. It must be the pointer you got from malloc. So this would also be caught by Valgrind.
Yep. Double free. So if you free something and then you say, okay, I want to free it again, this also doesn't work because it was already freed. It will tell you this. It will also tell you invalid read or write. So this means you have an array of size 5 on the heap and you want to write to the 6th element or you want to read from the 6th element. Then it will find this mistake. And yeah, the uninitialized variables. Yeah, how to use Valgrind. As with any debugging tool, you need to compile with -g. We have here written the command below. We probably did tell you only that you need to write Valgrind and your executable, so I don't know, A2, A3. You probably should also include this --leak -check equals full, because then you get a better report at the very end. And as we already told you several times, this Valgrind is also running when you test your program. Whenever you execute make test, then not your program is directly run, but it's run within Valgrind such that we can detect memory errors. Yeah.
And we'll see how to exactly interpret these errors Valgrind throws at us soon with the next example.
Yeah. Well, this was all the preparation, and now we're at the point where we want to be. Yeah, everything you need. Maybe, yeah, the next slide is maybe, I don't know if I should put it like this here, but we will show you now an example. More or less a complete guide on how to deal with memory allocations, how to deal with malloc, how to deal with realloc, how to deal with free. If you follow this guide exactly, you will not receive point deductions for memory management on A3. We are very sure about this. If you do not follow this guide, we are very sure that you will lose points on A3, because this is a complex topic and it's very hard to make everything right. And our experience from the last years really show that a lot of people get point deduction due to memory management on assignment 3. And that's why we want to prepare something to you that you can use, where we do everything right, hopefully at least. But we really try to do everything right, that you can use it for your assignment. And you also don't need to cite this example, because that's the way how you should use memory.
Maybe 2 notes to this. The first thing is that it's not like we will deduct this 25% of your assignment description if you see you didn't follow the guide. If you're not following the guide, then very, very likely you will see memory errors in Valgrind, or there will be situations where the program doesn't behave correctly in some edge cases, even there might be the case that our test cases do not cover these. But we will look out for these. So your memory management should really be on point and exact, because if you forget something of this, it could go very wrong. And the second thing I want to say is that, so we'll program the example now and we'll do some mistakes and then fix them later. So maybe not follow the example how we do it here, but then the final example code where we fixed all the errors.
And I should tell you from David that this also holds for assignment 4 and not just for assignment 3. So you have 2 chances to make something wrong here. So it's even more important to follow the guide. Okay. Yeah. 2. It's 2.
Okay.
Yeah, it should hopefully large enough.
No. Where can I copy it, or can I?
You will need the constants. Yeah, we will write them there. So in this example, we will now start by just creating an array. And we saw this before, make it the size of 4.
Yeah. So of course, if we use some size, some constant, we always create this constant here.
And we need to the cheat mode. this was not the right thing. Let me do this for you. Yeah. Okay, now we make it more like a game that you are the student, I'm the teacher, and you make the mistakes and I will clarify everything. And yeah, basically I would ask you to create now an array that we can store 4 integers. Okay, integer array, 4 integers.
Yeah, maybe I should try to also do something with this array, right?
Maybe we can even write a for loop over the array and fill in some values there. Maybe you can even write a for loop, one more for loop where you print the values.
Mm-hmm. Oops, caps lock. Maybe some spaces.
Something like that. New line. Okay, so you created the malloc array, you have a for loop where you set the variables, we print it, now we compile it. Yeah, compile it, no, everything
Let's
fine.
run it.
Let's run it. 0, 2, 4, 6. You inserted I times 2, so this is 0, 2, 4, 6.
So I think I've done everything correct.
Okay, maybe you want to be the teacher. What is wrong?
Yes.
The memory is not freed. Yeah. Other guesses? So yeah, I mean, this is obviously correct, but other guesses what could be wrong?
Yes. I need to multiply by size of integer.
So maybe go to the slides. Yeah.
Yeah. Or maybe we don't want to guess this and try Valgrind.
Now maybe go to the slides. So what we have done is the following thing. We allocated size times many bytes. So size was 4. If we go to the example, the size was 4. And size 4 is the size of an integer. So we just created the space for one integer variable here, but we actually wanted to create an integer array of 4, of length 4. So we need 4 times 4, 16 bytes instead of 4. So we basically just have this array down here pointing to this single memory location. Okay, and as you said, now the question is, how can we actually see that we did the mistake? Because here, when we just run the program, everything seems to be fine, everything works. And now if we maybe compile it, with -g, so for debugging, and run it now with Valgrind, what we have shown you before, so is it called main. Then we can see here 7 errors, and then maybe here, so we will start at the very top, we have here the line invalid write of size 4 at our main function in line 12. So this is here. This address is 0 bytes after a block of size 4. Yeah, so here it tells us we only allocated 4 bytes instead of 16.
And we're trying to write directly after it, so 0 bytes after.
And this memory block was allocated by the main function in line 8. So this malloc caused the problem here at writing. So we can find this problem very easily. Okay, then please fix. Now we always switch the keyboard layout. So we have size of integer times size, and maybe you can compile it and run it again. without Valgrind. This looks again fine, and maybe run it with Valgrind. Compile it and run it.
Oh, sorry, I only compiled.
Okay, now we have just one error in the very bottom line in the block. We have just one error, so we fixed most of the errors already.
So,
And we switch now to the visualization. And now we really have the correct sized array allocated. So we have these 4 integers. Okay.
okay, and if we read from the top, we can see there are no errors up until we print our numbers. But then down here, there's still one error.
And now we read just through the next error message, and it tells us
Down here in the heap summary, we had 2 allocations and 1 free, okay? And 16 bytes in one block are definitely lost.
what this means. We lost 16 bytes throughout our program, so we allocated 16 bytes and we never freed the 16 bytes.
And it seems like we allocate them in main.c line 8. So you can see here, okay, this malloc was never freed.
Yeah, so maybe we can free the memory. Okay, memory is freed. Run it.
Oh,
Very interesting now.
Okay.
Now we really got garbage values here. What did Julia do wrong? Yeah?
yeah.
The free is too early. Yeah, this is correct.
We can also check again with Valgrind. We have again these invalid read errors because we are again now reading line 15. Oh no, it says that they were freed at line 15. And at line 19, we're trying to read from them.
Make it that we can read everything. So invalid read of size 4. We have now 3 information here. Where this read occurred in line 19, where the address was, so it was already freed, and it was allocated at some point before.
So notice a difference here that now it says the address we are trying to access is now inside a block that was once allocated, but is already freed.
And again, yeah, we can defer from this information that the free was too early. Okay, then maybe we can put the free in the correct position. And yeah, maybe we open the visualization. So now we have the correct malloc, and now if we do the free, then we see, okay, the pointer still points to this memory address, but now marked in red, this memory address is now freed. So we should not access it anymore. But before, when the free was too early, we could access the memory location very easily. And okay, there was some garbage values in the memory, but maybe there would have been the same content as before. How could we know this? And how could we know this even without Valgrind? So give it one more try. So we put up the free again. And now we say that my array is a null pointer. So we write my array equals null. Okay, then maybe compile it. Maybe run it. And now we get something completely different. Now we get a segmentation fault, as you can see this here. And this does not occur when we run it with Valgrind, but this really occurs when we run it directly. Yeah? Is this now good or bad? This is really good, because whenever your program crashes, you know that you did something wrong. If you do something wrong, but your program does not crash, then how should you know that you did something wrong? But if your program crashes, you know there is a mistake somewhere. So this is really good if your program crashes.
And you can find where the segmentation fault happened if you just started with a debugger or also with Valgrind. So if you started with Valgrind, it also tells you at line 20. So here, our program crashed.
Why is this the case? So basically, my array is now null, and null is just the address 0. And if you want to dereference an address very close to 0, so 0 itself or 0 plus 1000 or something, there is really a protection mechanism that does not allow you to dereference such addresses exactly for that reason, because now we can use this as a tool whenever we do not use a pointer anymore. So in particular, after freeing it, we set it to null. And if we use it later on by mistake, then our program crashes. And we know, oh, we used something which we're not allowed to use. And that's why we always want to set the pointer to null after we freed it. Because then we see that we did something wrong. Now, yeah, perfectly. We put it down again. And if we have now the situation that the free is on the correct place, we have a visualization for that. Then we set the pointer to null. It's pointing to the address 0. It does not point to the heap anymore. And we cannot access this memory which we do not own anymore. So this is really, really convenient tool, and we should do that.
Yeah. Because when you access memory that we have already freed, basically anything could happen.
Yeah. Maybe we can demonstrate what happens if we free something twice.
Maybe it won't happen like this because it's very obvious that we are freeing it twice. But if you have some complicated program and somewhere you free your memory and then in some edge case you free it again, yes, we can demonstrate if you run this, then you also get, just by running your program, this error that you tried to free something twice.
And again, this error message is not very expressive. You don't know what you freed twice. And yeah, as you already prepared, if you run it with Valgrind. Then we also have here the detailed information where this invalid or double free occurred. And yeah, in which line it was allocated, in which line it was freed, and where the double free happened. So this is really convenient to use.
Okay.
Okay, so we remove this double free, we set it to null. Maybe we can show the whole code. Maybe we can run it with Valgrind one more time, that we can be sure that everything is correct. Yeah, so in the very bottom, 0 errors. Is now everything fine?
Okay, so the question was what about the typecasting here? Because I think I did something like this on the slides. Yeah, this doesn't matter. With or without this typecast, the same things happen. I just wrote it to be explicit what happens here, so that this malloc returns this void pointer, but we're assigning it to an integer pointer. So this is not a problem.
It's printing somewhere upwards the report.
And if we execute it just without Valgrind, then we can better see it.
So, any more one more
Before you corrected the malloc size, why could the program still run correctly? Was the input still true? 0 to 46?
Okay, so why did the program work correctly before I corrected the size here and we allocated too little memory? Well, it is just luck that our program happened to work correctly. Basically, by chance, we wrote into memory that we already owned, and it didn't cause any further problems. But it could also happen that you if you do too little here, write somewhere, and then either overwrite data that belongs to you, so from another malloc, or something else that might be more crucial, some libraries or some other codes allocated.
Now, imagine you have an integer array like this, and then you have a character array. You allocate it later on, and the character array is immediately placed after the integer array. And if the integer array is too small, then they overlap. And then you write to the same memory from the character array and from the integer array without knowing that you write to the same memory. And we didn't do this, so in our case this worked, even if the memory was too small.
Yeah, and it could also happen that your program just crashes if you write to memory you don't own, but this doesn't need to happen, as we've seen. It could just work, but it's still a problem.
So somebody guess what is still wrong? Yeah?
We have to check whether the malloc was successful.
Yeah, so the answer was we need to check whether malloc was successful. And now this is really crucial because everyone who is not watching this lecture will, 80% of the cases will do the mistake in the assignment. You need to check every malloc for null. Okay, so
let's try it. What happens if we don't do it?
Okay, let's try first what happens if we don't do it. So Julia will create now a constant which is really, really large. So this is just a multiplication that it makes it simple for us to write a very large number. But
so
basically,
I think now I'm at terabyte. And maybe let's try 128 terabytes.
So she wants to allocate 128 terabytes of memory. So this is like larger than every RAM that's ever created. You don't need the semicolon at the very end. So if now want to really allocate a lot of memory, like maybe my computer crashes now, I don't know.
Okay, so let's try it.
Compilation work.
Oh, we got the segmentation.
Oh, my computer at least did not crash now with this 128 terabyte of memory that we allocated. But we got the segmentation for it, and we need to do something about it.
So let's see where it went wrong with Valgrind again. Apparently, at a line 13, we tried to write to address 0, so the null pointer. And here we see this crashed and terminated our program.
Okay, and why did we get the null pointer? Because, as you correctly said before, if malloc cannot provide us the memory, then it will return null. And we need to check whether the pointer that we obtained from malloc is null. So maybe we implement this check and check whether my array equals null.
And then just return something.
So in this case, we cannot do much more because we have no memory left. We don't know really what happened there, so we need to basically terminate the program.
Yes, so now nothing happens. Maybe we could print something. Yeah.
So in this case, we really got null as the return value of malloc. We did check it, and we can print an error message and terminate the program. Yeah, but we need to do this for every malloc.
Yeah.
So, and if you write now instead of crash program, just the size again, and then this should hopefully not influence our program. Still, everything works correctly.
Mm-hmm. But maybe one array, or do we have a visualization?
No, we don't have a visualization for that, I think.
But maybe one array is not so useful, and we want a second one.
Okay, so we create now a second array.
Yeah.
After the null check, maybe, check. Or maybe you can demonstrate now everything you learned and do it correctly for us.
Okay, and we need, of course, because we are allocating something, we need again the null check. I just copied this. I'm lazy. Okay.
Yeah, no, maybe can we see everything in the program if you make it very small?
But I forgot to free it.
Okay, you forgot to free the memory, so my array 2 also must be freed. Okay, so we allocated it, we freed it, we did the null check. Everything right? Something wrong? Any opinions? It's a hard question, yeah. So
let's try to debug it with Valgrind.
Yeah, debug it with Valgrind.
Maybe execute it, okay. This worked, but this doesn't mean anything. Where was Valgrind? Here. Oh, 0 errors.
This also works.
So maybe we did everything correct.
Okay, now I'm a very mad person and I say, okay, in the second malloc, please use the crash program constant instead of size.
Here.
I want to test whether your out of memory in the second case really works.
Yes, it works.
No, it doesn't work. Yeah, run it with Valgrind. And we can see there is one error in this case. And maybe we can view up the error message. So what do we have here? We have 16 bytes in one block which was lost and which was allocated in the main at line 9. Yeah? So the first malloc call succeeded. We got the memory. And the second malloc call failed. So we had some memory allocated before, which we need to free no matter in which way the program terminates. So we also need to free the memory from the first malloc if the second malloc fails.
So do I need to free my array 2 also?
So my array 2, must it be freed or not? Maybe you can answer, some of you.
Do I need to do this?
The second free here, yeah? Yeah. This is correct. It must not be freed, or it does not have to be freed because it's already null and no memory was allocated.
Because if we're in here, we know that this is just a null pointer and we don't need to free the null pointer. Okay.
So maybe run it one more time with Valgrind. But now it should. So this works, yeah, and with Valgrind, it also works.
Yeah, okay.
Okay, then changes to the size again. So this is really fine now. And you see, this is not simple because we have the malloc, we need the null check, we need to consider to free everything if some malloc failed. After freeing, setting it to the pointers to null is also beneficial. It's really a lot of things that happen here. We also have the visualization for the last thing now. So if we have these two malloc calls, then we have 2 pointers on the stack pointing to 2 different arrays on the heap. And now if one malloc fails, then we just get the null pointer returned. So we do not obtain a second memory block, but just one. But the first pointer is still pointing to the heap, to some memory marked in green. So this is active. We need to free it. And if we terminate the program in this case, then the memory is not freed. And now the correct behavior would be then again to free it. We can continue, free it, and maybe also set the pointer to null that we cannot access the memory. That's not so crucial in this case, but the important thing is you need to free the memory. In any case.
Mm-hmm. Yes. So what we could do here is we could set my array to the null pointer because we freed it. But I think here it's not that necessary because we're returning directly after So I think there are not that many chances to use this freed pointer.
Yeah.
So I wasn't an error in the second malloc or before I tested with size second malloc there wasn't an error, but then with the big number, I don't know the anymore, there was an error. Why is there the difference that regarding the size it's an error? Not because when you do the second malloc you always need the num check with the array. And so I'm confused why the constant changes if there is an error or not.
Okay, so I think the question was why, if we forget this 3 in this null check, Valgrind doesn't show us an error if we just use it with the size and without this big constant. Well, Valgrind only observe the path our program takes during execution. So it sees, okay, this malloc worked, we iterate over it, we print something, and then it sees, okay, we free both arrays and everything is fine. So because we did free both of them, but this code in here was never executed, and therefore Valgrind couldn't see the error. But after we changed this here to the constant, so that malloc returns null, then we go into this if, and then we return without freeing the array, and then Valgrind sees, we didn't free this array. So Valgrind really just shows you the errors which actually happen in the current instance of your program that is running. So if you have an if else, and only in one of both cases you cause an error, then only when you actually visit this case, when executing the program, Valgrind will see and show you the error.
So more generally speaking, if you test your program using Valgrind, then it's not enough to test it for one input. You need to test it more or less for every input or every type of input, because if you handle inputs with in different manners, then your program takes different execution paths, and maybe in one part you're missing the free and in the other part you're not. So I don't know, in assignment 2 you start Wordle and you forgot, you allocated some memory, and when the word, the solution was not of correct length, you stop the program immediately at the beginning, and if you forget to free there, this Valgrind only sees this if this case happens. If you just test your program with correct inputs all the time, this will not happen, and Valgrind will not see it.
Okay, so
now,
let's
remove the second array. We have something better for that. We maybe could just increase the size of the first array and double the size of the first array.
Yeah, okay. So realloc, and then we need to specify the pointer. I want to increase my array by how much. We need to specify the new size.
So not an increment or decrement, you really write what it should be.
And I want to double it, so I write ×2. And because I paid attention, I know that realloc could move around my memory. So I actually need to update my pointer.
My array,
my array could now be somewhere different. With realloc returns a pointer to this new location, which already has my data, but I need to somehow store this data. So let's store it in my array.
Okay, run the code. This works. We're still just printing the first 4 elements, but it doesn't matter. Valgrind is probably more important. 0 errors, everything works. We also have a visualization. So we have the realloc. So marked in red below there was the previous array, and this was deleted. This does realloc automatically, as we learned before, so we don't need to free it. We get the pointer to the newly allocated memory. In this case, this memory block moved around, and yeah, it seems very fine. Okay.
Maybe let's try this constant here with the realloc.
Yeah.
So instead of this, I want to make my realloc very big, too big.
So that realloc fails. Now let's see what happens then.
Okay, we now seem to get some error.
So maybe we ask, before we execute Valgrind now, why do we get this segmentation fault now? Yeah?
Yes.
Yeah.
Yes, because realloc returns a null pointer. So let's check with Valgrind. And yeah, we have this invalid write at line 20 again to this null pointer.
So address 0x0 or 0x, and where something very small, 2 digits, 3 digits, is always a null pointer dereferencing. Okay, so yeah, you forgot the null check on the realloc.
But we've already seen this, so maybe, yeah, maybe I need to free it and then return 1 again.
But does it do it automatically, the freeing?
Yeah.
Just remove it for now. But print an error message.
It's null, okay.
You can't free my array, it's null. Yeah.
No. Okay. Let's try Valgrind.
And yeah, we got 1 error. And yeah, you teased it a bit before. Yeah, we still have the old array in the memory. So maybe move to the visualization. So when realloc fails, this is the situation here. Yeah, we still have this array on the heap. This is active. We need to free it before we terminate the program. But our my array contains now the value 0, so the null pointer, because we took the return value of realloc, assigned it to my array, and this now has the values null, and we completely lose the information where the original array was.
But we somehow need to free it, because realloc apparently didn't free it. Realloc failed. We overwrote the address we had of this old memory with this null the realloc returned, and now we can't free this memory.
Solution, we implement a temporary variable. So we assign the return value of realloc to a temporary variable.
Yep.
Then do the check for the temporary variable. So the my array is unchanged, and the my array is then still pointing to the old block of memory, which we can free. And if everything is correct, then we can say, okay, my array can now take the value of temp. Yeah?
Let's try it.
So we have this large constant still contained, so out of memory is happening.
Okay, 0 errors.
Yeah, so this works. Now we kept the pointer of the old array, and we stored the return value of realloc in another pointer. We compared the another pointer, and we are then able to free the my array.
And even if something happens with the realloc, if something goes wrong, everything works fine.
Maybe visualization, we have one here. So this is the case. The one pointer points still to the array, and the temporary variable points to null, and we did not lose the information to the array on the heap, and then can free it. I think that. Yeah, so we can do this again, free it, set it to null, or doesn't matter, but we are able to free it at least.
Okay, then maybe let's try it with the correct size. This is not the correct size.
Yeah, again, also here, don't forget the size of integer.
And yeah, so we didn't. The Valgrind says it's okay, so we didn't destroy anything with this null check.
Yeah, so this works. And maybe highlight the code here again. We, of course, not at the last line. that
This one, okay.
we need to assign this temporary value then to my array, because otherwise we would need to continue with the temporary array, but we want to continue with my array, of course, so we need to assign it here. And now we have a pointer which we do not use anymore, the temp pointer, so we can set this temp pointer to null.
Yeah.
Maybe write this in the code. We want to do it precise, so we make it precise. Okay, yeah?
And we also don't need to free the temp pointer or the my array if everything goes right, because realloc already freed the old memory block.
We again have a visualization for that. So if the realloc is correct, then the temp pointer points somewhere on the heap to the new memory allocation. My array still points to the old memory allocation. And if everything is fine, we can then assign my array to the same address of temp, so both pointing to the same thing. The old array got freed automatically from realloc, and then we set the temp pointer to null because we don't need it anymore, and we just have the my array pointer to the correct array. Okay, I think let's again open the code. We go through it one more time, what we did, but this is now complete. So we had this malloc in the beginning. And when you use the malloc, you need to check the return value. You need to check for null. Otherwise, 25% of your points are gone. Realloc, you need to assign the pointer to a temporary variable. Otherwise, this out of memory is not correct. And then you need to check whether the temp pointer is null, and you need to free all previously allocated memory. In particular, this includes the array that was there before you did the realloc.
Yeah, very common mistake at the assignment is not using this temporary variable, and then of course you can't implement the null check correctly.
Yeah, 25 of your points are gone. Yeah. And then when it comes to the end of the program, you need to free everything. Yeah, you need to free every memory allocation that you had. Of course, we just have one free because we did the realloc. So we don't need to free both the malloc and the realloc because we increased the size of array, but then the final pointer that we had, we need to free it again. And this is not true only for the very end of your program. This must happen in every case your program can terminate. Yeah. So also in the out-of-memory cases, you need to free everything you allocated before. Okay. So we have the code, and now again, what I said in the code, I just want to say it one more time. Malloc, do the null check and free everything before. Realloc, assign the return value to a temporary variable, check the temporary variable for null, free everything, including the old array, terminate the program. And when everything is fine, then you can assign the temporary variable to the correct array and maybe set it to 0. Yeah? And for the free, please free really every pointer that points to some array on the heap. Just once, don't free it twice. Free it once, and it's good practice to set the pointers to null afterwards, because then it's more easy to detect errors if you do some of them. You very gently skip the two-dimensional arrays. This is enough for today.
Yes. So as we have seen, the stack was really nice to work with. The heap is not so nice, but maybe it also gives us many benefits. We need to keep track of this free. We need to keep track of what all of these functions could return, how we can check it in every way, how could our program terminate. We need to free everything. So this can quickly lead to errors, but this gives us the ability to actually manage our memory, to really hold on for our memory as long as we want, and it not automatically gets deleted when we return from a function, but we can keep it as long as we want. And also we can resize our memory, so we can actually increase an array after it was created, which is very powerful and you will need.
And then please follow our guide for assignment 3 and assignment 4. Please do it.
Yes? If you use the heap on assignment 2 and you didn't do any null checks, for example, or you didn't free your memory, then yes, this will lead to deductions because it will lead to Valgrind errors.
But we will not be that strict as we will be on assignment 3.
Yeah.
But for assignment 3 and assignment 4, it really must follow exactly this pattern. Any further questions? Everyone is a bit anxious now about that. Otherwise, if some questions pop up in the next 10 minutes, you can ask in the break, of course, and in 10 minutes, David will start with the lecture. Thank you.